One, two. Yes, okay. Can I close the door? Yeah, good morning, everyone. Let's start our exercise class. So first, as Lydia promised in the lecture, I'll start with the Fourier transform recap, and then we'll apply, and then we'll consider the exercises in the new exercise sheet. We'll implement our knowledge basically about the Fourier transform to the position and momentum basis. Okay, so what is Fourier analysis about? Basically, the one motivating example is let's consider different musical instruments. Suppose that you have a guitar and then you have a violin, and then you can play the same note, which corresponds to a particular frequency on the guitar and on the violin. However, our human ear is able to distinguish the sounds when and say, okay, this is a note produced by guitar, and this is a note produced by a violin. So how does our brain do that? So basically what our brain does, like it's somewhere in the background, it runs a Fourier transform. Because the instruments, they create vibrations in the air, and our ear perceives the sound waves. And basically a certain pitch, we hear a certain pitch at a certain volume. But the sound is formed not only by the pure wave, which corresponds to the note itself. So let's say this is a wave which corresponds to our note with a particular frequency, but it also has additional frequencies, which are called a timbal, which correspond to the harmonics and overtones, which are specific for each musical instrument. So let's say, yeah, for guitar, maybe we have some additional frequency wave here. And for the violin, we have something else. And so what our ear perceives in the end is the combination of the several frequencies, and our brain is able to decompose the initial sound, the sound signal that we get, into these frequencies. And this is basically what the Fourier analysis is about. It's about decomposing the wave or the function into its constituent frequencies. And again, we can use here the linear algebra analogy, which is very useful. We have a certain function, and then say we know that there is a basis in which this function can be decomposed, and then we decompose this function according to this basis. And the Fourier coefficients would be just the decomposition coefficients in this basis. Okay, so to start off, let us start with the simple examples of functions for which this is more or less straightforward. So we will start with Fourier series. So all the results I present here, I will not give any proofs for these results. The proofs and all exact conditions on the functions you can find in, I guess, analysis 2 course or so. But here I'll just present the results basically. So suppose that we have a function f, which has a period 1. So the period 1 means that f of x equals f of x plus 1 by n for any x and any n. Yeah, and then and for this function, we know a following result. this function can be decomposed in terms of sines and cosines. So it can be written in the following way. So sum over ON from minus infinity to plus infinity, AN sine 2 pi n x plus Bn cosine 2 pi n x. So this is a result from Fourier series analysis. So basically here you can just to make a sanity check, you can just simply check, oh, if this function indeed has a period 1. But this holds trivially because sine and cosine are periodic functions, in this case with a period 1. Okay, so then let us see how we can go from this to the Fourier transform with a complex exponential. So what we can do, we can just represent the sines and cosines in terms of the complex exponentials. And yes. So this is a result I'm not going to prove. The way you can see it is, okay, so basically you consider the space of functions with period 1. And then there are two functions, sine and cosine, which also have, and so these two functions, sine 2p n x and cosine 2p n x, also have period 1. And basically, then the idea is that the first you prove that the space of these functions, this is the orthonormal basis in the space of these functions. And then from that, it trivially follows that you can decompose this function into, with regards to this basis. But this is a result which is usually proven in series analysis or so. Yeah, so I think it's also on Wikipedia, so you can just look it up. Okay, so here we just rewrite sine in terms of complex exponential. So this we've already seen. So it's e to the power I 2p n x minus e to the power minus I 2p n x over 2i. And here cosine is e to the power I 2p n x plus e to the power minus I 2p n x over 2. Okay, so then let us just substitute them here. So what we get is an e to the power I 2p n x minus e to the power minus I 2p n x over 2i plus bn, the expression for cosine, over 2. Then now let us regroup the terms in this expression. So first we combine the terms in front of e to the power I 2p n x. So what we get here is e to the power I 2p n x. Yeah, from the first term we get an over 2i. From the second term we get bn over 2. Yes, then we combine, put together the terms in front of e to the power minus I 2p n x. And what we get is minus an over 2i plus bn over 2. Okay. So now we'll continue on the other board. Okay, now what we can do is, so suppose that, so here you have two sums, right? So this is ranging for, so here you have the sum of two terms, and it's ranging from minus infinity to plus infinity. Now let us, in the second term, substitute minus n by n, basically. So what we get here would be the sum I, 2p and x, and here we'll have an over 2i plus bn over 2, plus b minus n over 2, minus a minus n over 2i. And let us call this coefficient Cn. And what we get here is then sum over n, Cn e to the power minus 2pi, so I by 2p, so plus I by 2pn x. And this is basically the Fourier series. So again, nothing magical happened here. We just rewrote the initial sum in terms of sines and cosines, in using the complex exponential. Yes. So I mean, so this is just a trick here that we do. To basically, yes.
A1 to A10 are coefficients. So what does A minus mean?
I mean, so here the coefficients range from minus infinity to plus infinity. So basically, then your A's and your B's go from A minus infinity. So basically, go up from to A minus 10,000, A minus 1, A0, A1, and so on. So basically, yeah, they just range not only over the natural numbers, but also the other side. Make sense? Does it make sense? Yeah, okay. Okay, and this is very similar to what you already saw in the lecture, how we made a transformation from momentum representation to a position representation and back. But there we have the continuous basis, so we need to basically substitute the sum by the integral. But let me first elaborate on how this goes. Okay, so these coefficients Cn that appear in this sum, they're called Fourier coefficients. And of course, their form depends on n. So Cn depend on the function f that we are trying to decompose. Okay, so, and sometimes they're also just denoted as f. Yeah, can denote as f hat n to stress their dependence on the function f and the number n. Okay, so then we have the following expression. I'm just rewriting this Fourier series. And now the question is, so now theoretically we know that because cosines and sines form the basis, then we can rewrite this in terms of the Fourier series with a complex exponential. how do we actually find the coefficients in this decomposition? So to do this, let us do a simple trick, which is let us integrate both sides of this expression, adding the term e to the power minus I to p kx. So we just integrate both sides. So the first side, and we integrate from 0 to 1, f of x e to the power minus 2 pi I kx dx. And this should be equal to integral from 0 to 1, this coefficient e to the power I 2 pi x n minus k dx. And so basically here something funny that we can see here is, for example, if the n, so if we integrate this over x, then basically what we get is f of n comes out, right? Then we just need to integrate this complex. Yes.
Question one: what happened with the sum form? Because we're integrating using the left side, adding e minus 2 pi I kx.
Yes.
On both sides. What happened with the sum?
Sorry. Yes, I completely forgot. Here, right? Here we still have sum over n.
Okay.
Yes. Sorry. I was going too fast. Yeah. So here we still have sum over n, basically. Okay, so we have sum over n. Then we integrate this. So this is just an exponential, right? So this is e to the power I 2 pi n minus kx over 2 pi I n minus k. Right? Yeah, and this is from 0 to 1. So here then what we get is e to the power I 2 pi n minus k by 1 minus e to the power I 2 pi n minus k by 0 over 2 pi I n minus k. All right. Yes, so let us analyze this expression. So this is basically 1, right? So am I doing this correctly? Let me see, so it's 2 pi I n minus k. It's basically 1. I'll do it here, 0. Sorry, just a moment. So we integrate from 0 to 1. We get 0. Okay, yes. So basically what we get here is we would get here 1, right? Here 1. So generally we would get 0 in all cases. So we get 0 over 2 pi I n minus k. We'll get 0 in all cases, but we need to check specifically for the case when n equals k. Because in this case, something weird happens with the denominator. Yes?
Why do we get the 1 with pi? Because of sum.
So n and k are natural numbers. So they're either natural number or a number in z, basically. So basically, what we have here is e to the power 2 pi I by some natural number, and this is like we just do. If you imagine a complex plane, then you just do like this n times, and then you arrive to 1 anyway. So here we get this 0 for all cases when n doesn't equal k. Yes.
So question on complex multiplication. So I always wondered, like, if you have e to the power I 2 pi, like in this example, 2 pi x n is k, you could, if you're really using the commutativity of multiplication, you could say this is e to the I to pi n is k times x, and e to the I to pi n minus k is obviously always 1, as we just found out. So we have 1 to the power of x. And if x is not a natural number, but some real number, how do we determine the value?
So, okay, so what you're suggesting is if we have e to the power I 2 pi n x, this is equal to e to the power I 2 pi n x, 2 pi n to the power x.
Yeah, and then we have 1 to the power of x, with x being some real number.
Okay. So I mean, so with the complex numbers, you need to be careful with this. So for the complex numbers, this doesn't work basically. This rule, it doesn't really work. So because x is a number in between 0 and 1, right? So basically, here you kind of introduce here it is a point on the circle, a point on a complex circle, basically. So like this rule is not applicable here.
What rules are applicable? So what is not applicable? Commutativity of multiplication?
What exactly is not applicable? So here, I guess it also depends how you so even in the usual analysis, like not complex, not real analysis, when you define this, but you basically still define, you can still define the power of a number by its exponential, right? So basically, in a complex analysis, you can only work with the exponentials to some complex number. And in all other cases, you would just need to be careful.
Specifically, what am I not allowed to do?
So for example, you cannot write like x to the power I. Because, or can you? So basically, what this means would be x is e to the power log x. So you will be writing here is e to the I log x.
X is negative.
Then there are like special rules for doing it. So like I don't want to go into it. Some of these things are covered in the complex analysis, like how you take logarithms of the complex numbers. So there are some basically sometimes you cannot do it. Sometimes there are special values that are allowed, and sometimes they're not. But for example, here, this rule doesn't still, it simply does not apply. Because you can think about this exponential as, it's just a way to represent that, oh, this is the point on this circle in a complex plane.
So I'm not allowed to look, take something out of the vector space.
Yes, you can also see that this is, you can also kind of understand that this is not an exponential in a sense of like real analysis, but this is just the way we represent, oh, this is this point with the phase phi on the circle. And I mean, the rules, the usual rules, like for example, this, they apply, right? The rule with power does not apply, yes. So for example, e to the power alpha to the power beta is not necessarily e to the power alpha beta.
And this is only for complex numbers or also?
This is only for complex numbers, yes. Okay, so, and I mean, when we also have the exponential and the operator, this also becomes a bit more difficult. So you cannot write the exponential to the power of operator to the power of operator. This is generally not well defined, yes.
Excuse me. So does that mean I can do e to the power of I to by n natural number is just one? But what is the takeaway here? Because is it one or is it not?
So e to the power 2 pi I n is always 1. E to the power 2 pi I n by some x, which is not natural, is not 1.
The next question is why is it different from 0 to 1?
So here we integrate from 0 to 1 because we want to, because that will give us the answer. But generally, this works because this function has a period 1. And so, for example, like we got this this argument in the exponential, which is 2 pi nx, because we assumed the decomposition for functions with period 1. If it has a period 2, let's say, you need to scale this coefficient, basically, and then you will also need to integrate from 0 to t, where t is the period. But this is simply done from, can simply derive from this case by saying, oh, I just scale my x. Do you understand what I mean by scaling the x? I mean, okay, so by scaling, I mean that if you have a function f of x with period 1, then it means that the function f of x over 2 has a period 1/2. Right, so which means that any result that we can get for the functions with a period 1, if we just substitute x by half in all our considerations, this result will hold for the functions with period 1/2. So, okay, so back to our thing here. So here we see that the result of this integration is 0 for all cases, except for the case where n equals k, because this case we have to analyze separately. So if n equals k, then what we have here is integral from 0 to 1, e to the power I 2 pi x by 0. This is 1 dx. And if we integrate 1 from 0 to 1, we get 1. So what does this mean? This means the following, that the integral we were considering there, the integral from 0 to 1, of the e to the power I 2 pi x is actually 2 pi x n minus k, sorry, is actually a Kronecker delta of nk. Which, so by this, I just mean that it is 0 for n not equaling k, and 1 in the case when n equals k. So this is actually a useful result to just remember. So we got from integral from 0 to 1, e to the power 2 I by 2 pi n minus kx dx is equal to 0 when n is not equal to k, and 1 when n equals k, which means that it's just delta nk. Okay, so then what we got, just rewriting our initial integration, that integral from 0 to 1 f of x e to the power minus 2 pi I kx dx equals sum over n f of n delta nk, which means that the only term from this sum that survives is the kth term of decomposition. So hence, by this trick, we just shown that the kth term of decomposition can be obtained by integrating from 0 to 1, or generally over the period of the function, f of x with the coefficient e to the power minus 2 pi I kx dx. Okay, I hope this is more or less clear. And I didn't go into much mathematical detail in what restrictions we put on the function f itself. But this decomposition only works for reasonably nice f. So they have to be continuous, bounded, and so on. I don't really focus on this here because usually in physics, we assume that we only work with such reasonably nice functions. And again, coming back to our linear algebra analogy, basically what we did here, we took the function f and decomposed it in a basis of the complex exponentials e to the power I 2 pi nx. These were the functions with the period 1. You can ask what happens to all the other functions? Can we also analyze them in the same way? Yes, we can. So now let us consider a bigger subset of functions. So these are functions f, which generally map so real numbers to complex numbers. And we will first consider the functions with period 1. By the scaling argument, we can extend this argument to the functions of an arbitrary period p. And so you can in principle try to do it yourself, but what you will get is that these functions can be written as Fourier series of e to the power 2 pi I n over p x. And now we want to go from this to the functions which are not periodic. So if we take a function which is not periodic, in principle, it can be seen as a function with a period infinity, or it can be seen in the same line of thought as a limit of periodic functions, fk, fk. So say we have like the sequence of this periodic functions with periods pk, periods, which is getting larger and larger, and in the limit pk goes to plus infinity as the k goes to infinity. And like taking this limit, we can expand each of these fk's as we did before. E to the power 2 pi I n over pk x. And basically, and these exponentials, they're evaluated on more and more kind of densely packed points. And so from this, considering this just sums over n, in the end, when taking this periods pk to infinity, what we get is basically continuous linear combination of this elements in the sum, which in mathematical terms just corresponds to us changing the sum to the integral. So the result then is the following, that we take, again, reasonably nice function f, which is in general case not periodic, then we can decompose it as a following integral. So we can write f of x as an integral from minus infinity to plus infinity, f hat of psi e to the power 2 pi I psi x d psi. So how do we find out the coefficients f hat of psi? This is, we can be inspired by the formula, which is up there. And one can also derive it in a similar way. And we can write that f hat of psi equals the integral from minus infinity to plus infinity, f of x e to the power minus 2 pi I psi x dx, because this is also similar to the term which appears there. So this also shows an interesting property. So basically, if we write that the function f, and this is sometimes the notation which is used, yes. So I'm not going to prove it here, but in principle, what you can do, you just follow the same way we proved that formula. But now you just have to integrate this from -infinity to +infinity, and also add the term of 2 pi I of minus 2 pi I, x minus 2 pi I psi x, basically, and integrate. So the function f hat is the Fourier transform of the function f. And from and then we also write that the function f is the inverse Fourier transform of the f hat. So here you see that in our definition, to perform a Fourier transform is to basically multiply the function by 2 pi I. So if we have a function f, to get its Fourier transform f hat, we need to use this formula. So we multiply by minus 2 pi I psi x and integrate. And to perform the inverse Fourier transform, we have to multiply by 2 pi I psi x without the minus, basically. So some examples. Yes.
I remember that you could write Fourier transform factor of 1 over the square root of 2 pi back and forth formations.
Yes.
Why is that there? I don't know myself where it is. But I thought it had to be there so that we get back.
So this is a very good question. So for the cases where we've seen the transformation of from the momentum basis to the position basis, we also require that the functions which we transform are normalized, which means that the integral over modulus psi squared dx is 1. Then what we have to do, we have to, in the Fourier transform itself, also impose these coefficients. Let's say like this: alpha here and beta here, which make sure that the transformation preserves this normalization condition. But like when you think about functions in general, this is not a general requirement, right? So in this case, if we don't require that they're normalized, this alpha coefficient can just go into the function f of x. But because this is exactly because of a normalization condition, and this prefactors of 1 over square root of 2 pi, they can also be chosen in a different way. So for example, you can say, oh, when I do the Fourier transform, I choose the coefficients 1 over 2 pi I, sorry, 1 over 2 pi. And when I do the inverse, I don't need any coefficient anymore, because this coefficient is already encoded in the direct one. But we choose kind of over square root of 2 pi because we want these coefficients we want this to be symmetric in some sense. But yeah, generally these coefficients appear when we impose more conditions on the functions that we transform. And we actually will see it when we'll start looking at the exercise sheet and we'll calculate this coefficient. But some examples, some of them one of them is quite important. but the first ones are just for fun. So for example, we have a function f of x, which is e to the power minus 2 pi modulus x. So for example, the Fourier transform of this function would be f hat of psi would be 1 over pi 1 over 1 plus psi squared. Or f of x, for example, you can take another function 0, which is 1 when modulus x is less or equal than 1/2, and 0 when it's 0. Then the Fourier transform of this is sine pi psi over pi psi. So why I'm making these two examples, which seem to be a bit exotic? Well, one reason is that these are functions for which you can just easily take the integral and calculate the Fourier transform yourself, basically. So this is easily analytically solvable. Of course, when you have a general, some ugly function, you need to use some computational methods to calculate its Fourier transform. And finally, the other function, which is also can be solved analytically, but it requires a couple of tricks. And you can actually look it up on Wikipedia, how these tricks are performed. So this is function phi of f of x, which is e to the power minus pi x squared. And the funny thing about it is that it is its own Fourier transform. So its Fourier transform is f hat of psi e to the power minus pi psi squared. And this is going to be very important when we start looking at the Gaussian wave packets, because the Gaussian wave packets have the shape of the Gaussian. And this is basically the Gaussian. So e to the power minus x squared, all the functions of this type correspond to so-called Gaussian distribution. And there we will see that when we go for the momentum representation, and if it's a Gaussian wave packet, then if we go to the position representation, it's also going to be a Gaussian wave packet. So this is kind of a good thing to remember, that the Fourier transform transfers Gaussian into Gaussian. Okay, so I think we can make a break now, and then in the second part we'll apply our Fourier analysis knowledge to the position momentum basis.
Yes, this is not those two. It's not by the T2 is not centered, so you have to play dot shift. Oh boy. Did you see the view map? No, literally computer line. I was like, oh, if I'm stupid, like, who would I know that?
Yes.
Tiny question. So the f dash function is the coefficient function analogous to the discrete case.
Yes.
And if we multiply them in the integral, we get this function. And the second question is regarding the e to the log thing.
Yes.
Can't do that thing because, as we just said, that it's not the same. If we have like I to the power of x, we can't say it's e to I ln x because the multiplication rule, as you said, doesn't work.
Yeah.
So how would one power complex numbers?
Good question. this is covered in the second part of a complex analysis lecture, which I never
Don't we have to do in some exercises powering of complex numbers?
No. So the way we use complex numbers in the quantum theory is we just yeah, exactly. So like for all the others for all the other stuff concerning the like how we take a logarithm of a complex number, how we represent the power of the complex number. So in principle, these things can be done. The problem is that this is covered in the complex analysis course. And to be honest, I've never used it after that. So I actually don't remember very clearly. I know that it's a bit tricky. It's yeah, I think
the I we can power easily just by multiplying.
Yes.
But the other ones we can't represent through e to the I power.
Yes. Like yeah. Yeah, sorry, I cannot like help you in this case.
Yeah, it's expensive. It's a huge $4,000. Yes. I mean, yeah, I didn't, but it isn't going to be so like if you need to no. But I don't know, man. I feel like this is one. Yeah. You know that. Basically, you guys You get a lot of basically like space like so for example, if you like ice, but you're not spreading the place on the city, you get water. Okay, sure. So I guess you can probably. No, I guess. Pretty cool. Just like one yeah, especially small company, which is the first batch, so they already, yeah, it's a deposit. The order is November. Okay. Oh, they pay a fiscal cost, so they like, so you are sorry, the amount of pay for keep the tax on. Yeah, but it's good, they're really good. Yes, if you need more credit, you take over this. Right, sure. You get support. I'm also got anything. They give you the full guide and stuff. So I assume I have no, or I still have it, but I don't use it. All the noble. Big jump and battery just stopped working. Okay, we bought a new battery, Lenovo certified whatever. Bought the new battery, worked on it for like a few weeks, and then at some point it's like, nah, I don't like that battery, I won't charge it. Oh, is it like this checking of this year? No, it was a certified battery for what we said. So even if sure they do some check, but even if I just how I mean I think the battery was fine, even the old battery was probably fine. It was just the device. I was going to try my battery. It's like, okay, I don't like the battery, like I don't want to use it. So since then, I just took out the battery and run because if I have it plugged in, it's such a big, like it's a 17-inch like this big. So it's actually not really important anyway. So if I have it standing around or it's not, if it doesn't have a battery, you can't store the battery either. So. Sure. The reason that was being before so. And basically talking first of all, I live in Sao Paulo, University State, by the way, only practice 7 minutes, it's not there, 7 minutes. This game I response faster than my hobbies. Anyway, so he lives in somewhere for a long time with the people from ETH here of the yeah. He's also right and so point is he wants to let the crossover usually we go to my place with the But one guy, the group is also, yeah, okay. And usually you go to money. It's going to, okay. Well, it was a small house in fact, and there is a beaver and everything. But the only thing that's a bit is the seating. It's like the couch, and it's all just one couch, and then the bed, and the only couch is like comfortably four. If you're a bit cramped, okay, I guess maybe 5 or 6. You're set. No.
You are so long.
Yeah, five feet. So you look at the chair.
Okay, shall we continue? So now that we know a lot of stuff about Fourier transform, let's apply it. So back to our quantum systems and to the infinite dimensional continuous Hilbert spaces. And there, suppose we have 2 bases, which we call as position bases. And then we also introduce the momentum bases. And we've seen already that whichever basis we choose, if we have a state psi, which is in this Hilbert space H, then we can decompose it with regards to each of these bases. Or we can also do it in the P basis. So P, psi tilde of P, P. One question still remains, how are these 2 bases connected? So, and we impose the following, that they're connected in the following way. They're related by a Fourier transform. So to get the element of the basis P, we just perform a Fourier transform with the coefficient here, e to the power minus I, alpha px, x, and we integrate over x here from minus infinity to plus infinity. And because we also, this is not in any way guaranteeing that this is normalized, and we want the basis states to be normalized, we also include a coefficient beta here. And this is one of the ways we can define the connection between momentum and position bases. So the first thing that we're going to calculate is we're going to find out the coefficients alpha and beta. And the coefficients alpha and beta can be found from considering that the states of the bases are normalized, as I already mentioned. So which means that the bracket PQ is a delta function. So let us just write what this bracket corresponds to. So the first bra would be the conjugate of this expression. So it would be b star, beta star, integral from minus infinity to plus infinity. Let's take it over y, let's say, dy e to the power I alpha py p. I'm sorry, y. And the second part would be beta integral from minus infinity to plus infinity dx, let's say e to the power minus I alpha q x x. Okay, so what we get here is in front of the two integrals, we get modulus beta squared. Then we get two integrals, one over y, the other one over x. Then we get the complex exponential e to the power I alpha, so minus I alpha qx minus py. And then we get the bracket xy. We know that the position basis is also normalized, which means that this bracket is just a delta function, delta of x minus y, which means that we actually can get rid of one of these integrals due to the delta function and just assume, yes. Yes, you're right. Why? Sorry. Yes, thanks for the correction. Okay, so this delta function allows us to get rid of the one integration. So what we get is basically modulus beta squared integral, let's keep dx. And then here we just put y equal x, e to the power minus I alpha q minus p x. So I claim that this is in fact the following: beta squared 2 I over alpha delta q minus p. So, okay, so this is a bit of a tricky part. So when you look at this integral from minus infinity to plus infinity of this exponential, one way you can see why we arrive to this result here, or why we indeed would get the delta function here, is because if you roll your memory a bit back when we were considering the similar integral, but over the period from 0 to 1, we were getting that this integral would be non-zero only in the cases where q would be equal to p. But this was when we were considering the Fourier series of the periodic functions. So this should already give you a hint that this integral should be equal to something that is only to some object which is only non-zero when q is equal to p. So why it is a delta function? So if you try to analyze this integral mathematically, then just taking it straightforwardly, then what you will get that you would need to look at the limit of e to the power minus I alpha q minus px at the x going to plus infinity and minus infinity. And actually these limits, they don't exist because this is a complex exponential, and at the infinity will just oscillate basically. Yeah, its value will just oscillate because sine and cosine, for example, they don't have any limits when as x goes to infinity because they keep oscillating between 0 and 1. And the complex exponential is basically this combination of sine and cosine. But the way you can, and usually the way this is seen, this is not an integral, not a kind of mathematical integral, but this is an integral over the space of probability distributions. And so, but yeah, this is not the mathematics we're going to go into. One easy way you can see this is the following. So one of the consequences of this fact that the integral of this complex exponential is a delta function is that actually this means that the Fourier transform of the function, which is 1 everywhere, so you can just see this can be written as this, and this is basically the Fourier transform on this function, is a delta function, like up to this constant, which means that if you take the Fourier transform of the function, of the delta function, you should get this function 1. And basically this you can do by just saying, oh, the delta function is a limit of as n goes to infinity of this sequence of functions, and then find the Fourier transform of them, and then they take a limit as n goes to infinity. So when I was introducing the delta function, if you remember, in principle, you can see the delta function as the limit of a sequence of functions. So for example, you can see it as a limit of the Gaussian distributions, which just become more and more concentrated around the 0 value. So basically their variance would just get, as n goes to infinity, the variance would go to 0. And then if you take the function, take its Fourier transform, which would also be a Gaussian, and then take n to infinity, you would get that it would be a Gaussian to the power 0, so it would be 1, basically, up to this constant. Yes?
Right, this question is that function is limit of Gaussians formally, like.
Yes, I can. So this is, so one can, again, this is not very precise mathematically. Mathematicians will kill me because delta function lives in the space of functionals, but still, as a physicist, we can still see it as a limit of the sequence of functions, where, for example, you can take delta n as this Gaussian. And why we take the Gaussians? Because then it's easy to compute the Fourier transform. We know it's a Gaussian. So in the end, what we would get is, it would be like the integral of this delta n of x e to the power minus I, like 2 pi, what's there, x psi dx, and then you take as this goes to infinity, and then you get to optimization this 1, basically. So this is one way to see why this integral would give you a delta function. Yes. This one.
No, the delta function. You said the notation is not correct because delta function is a function, not a function.
Yes, you can also, like, yeah. If you write the delta of x e to the power minus I 2 pi x psi dx, and apply this delta of x here, right? So it'd be just e to the power 0, so it'd be 1. There are like several caveats here, which are mostly mathematical. So one of the caveats, I think, is the fact that like when you define this, when you look at the delta function in this integral way, this is also not like the exact correct way to look at it. So you will still need to, this is a delta which acts on this function, but this function is a complex. So it's a trickier to work with it. So it's still the correct kind of the semi-correct mathematical way to look at this is also as taking this and here and taking a limit. But as you correctly said, in principle, in this case, because in the end, we know mathematically that it works out of other arguments, we can use this argument with the x equals 0. But this is like more rigorous, more semi-rigorous mathematically. This is also due to the fact that, so here, by showing this, this integral and using the property of the delta function, we get that it's 1. And from this, we can conclude, then the Fourier transform of 1 must be delta, right? However, we only defined our Fourier transform for the functions f, which are kind of nice. So they go from real numbers to complex numbers. They are bounded. They're in some fashion continuous, and so on. However, this does not cover the delta function, because the delta function is not continuous. So basically, one cannot even define what continuity would mean for the delta function, which basically means that we need to, in the end, to apply the argument, we need to somehow convince ourselves that delta function is continuous. And the way to do it is to see it as the limit of these functions, which are clearly continuous.
Just make sure that this is not multiplication, mathematically speaking, between delta x and minus
Mathematically speaking, no, this is not a multiplication. Mathematically speaking, what we do here, we act with delta on this function. And the action in this case corresponds to integration, or we can write it as an integration. But generally it's just action, because delta lives in a different world than the function e to the power minus 2 pi x psi. Yeah. Yes.
So why does elastic flow equal here?
Which one?
No, not the map stuff. The stuff that you wrote down is actually the left side.
Oh, here?
No.
Yeah, here?
I don't get it out. I won't even try to complete what you talk about. Yeah.
Okay. Okay, so the easy kind of, the way you can convince yourself that it's true is by just looking at the Fourier series decomposition that we did before, right? And there we did this integral from 0 to 1 e to the power minus I. So the thing is, like, if you do the same thing here, you will not get anything, because the limit of these functions at minus infinity and plus infinity is not well defined. But this is a way to convince yourself that we also should get some object which is only non-zero for q equaling p. Yeah, so this is kind of not very mathematical, but like the argument just convince yourself that this works. Yeah. Okay. So we got this. All right, I didn't finish did I? Oh, yes. So in the end, what we got is that PQ would be equal to 2 pi over alpha beta squared delta of Q minus P. And this should be equal to delta Q minus P, because our basis is normalized, which means that 2 pi over alpha beta squared should be equal to 1. And here, there is a standard convention by which these coefficients are chosen, which is that alpha equals 1, and then beta choose 1/3 of 2 pi. And this is, and again, coming back to the question that was asked before, where does the square root of 2 pi come from? Here you clearly see that it just comes from the normalization condition. Okay, so maybe one small comment. So in theoretical physics, we usually kind of operate without considering any dimension of the variable. Yeah, sorry.
For the coefficients, in the script and in the lecture, we saw the definition of the momentum basis with the Planck constant as well.
Oh, yes, exactly what I wanted to talk just now. So we usually don't consider any dimensions, which means that we take all the fundamental constants, for example, the speed of light, the Planck constant, h bar, the gravitational constant, we just take them equal to 1 in all calculations because that just saves space. And in the end, we just add them by considering the dimension of the variables that appear. Like, for example, here, this would mean that alpha should be actually 1 over h bar, because what we have in the exponential, we have some minus I alpha px, and then the dimension of px is h bar, and we want our the argument of the exponential to be dimensionless. Yes. So when we talk about physical variables and we want to actually plug in the values that we get into the lab then each variable has a particular dimensions like NCI. So, for example, the momentum is kilograms meter by meter per second. Then the x, the position, is meters, and the Planck constant is NCI here, kilograms by meter squared over second. Does this make sense?
I still don't really see why or what another physicist say.
Okay. So what is the momentum? The momentum is defined as mass. So the mass. So suppose you have an object which is moving with velocity v, and the object has the mass m. Then the momentum of this object is defined as its mass multiplied by its velocity. So it's m by v, and m is in kilograms, v is in meters per second. And x is the position, so it's meters, basically. And then each of these fundamental constants, it has its own dimension. Yeah, so for example, I don't know if, so for example, the easy way to calculate the dimension of the Planck constant is to say that, actually the energy is the Planck constant by frequency, then the Planck constant is the energy multiplied by second, and then you just need to find out the dimension of the energy, which is mass by velocity squared. But the thing is, like, this just comes from knowing some basic connections between like these variables. The good news for all of you is that you don't need to know any dimensions here. So you in principle should remember that here, if we want to plug in the actual values for p and x, we need to use alpha equals 1 over h bar, and then in this case beta would be 1 over square root 2 pi h bar. But since we consider h bar equal 1, we don't care about it, and also we will not do any numerical calculations in a course. So this is good to remember. But if you, for example, don't write it and implicitly assume that it's 1, it's not a problem. Okay. So what are the properties of these two bases. So there is this one really interesting and important property which connects the position basis and the momentum basis, which is that they are mutually unbiased. What do I mean by that? If I take an arbitrary basis state from the momentum basis, and also I take an arbitrary state from the position basis, then their overlap actually, the modulus SQuID of their overlap does not depend on which states I choose. So whichever two states I choose from this basis, their overlap, the modulus of their overlap is always the same. And this property is called that being mutually unbiased. So these two bases are mutually unbiased. And we will prove this in a moment. Okay, so what we want to prove is that these two bases, X and P, are mutually unbiased. So we just need to prove that the modulus XP is equal to the modulus of X prime P prime for any X prime P prime. So in this case, this means that suppose that I have these two bases and I take any state from here, like I don't know which one, and any state from here. I don't care about which states these are, and I can always tell you the overlap, the modulus of the overlap between them. So by the overlap, I mean this bracket XP. So this XP bracket is basically a constant for regardless of which elements of the basis I take. So there is no kind of dependence on which X and which P I choose. And this is also one of the ways actually to define the position momentum basis. So you can just say, oh, these are two bases which are mutually unbiased. And from this, you can, in principle, arrive to the fact that they're connected by a Fourier transform. Okay, so this is fairly easy exercise. So given that we already done similar stuff, so we have X and P. And from the previous exercise, we concluded that P is 1 over square root of 2 pi integral from minus infinity to plus infinity e to the power minus I px x dx. Because it's just two. So the thing that I'm proving here is that this overlap does not depend on X and P, right? And Yes, but this is a continuous Hilbert space, which describes the position which ranges from -infinity to +infinity in R. So these are just the labels that we label the state with. Okay, so since I have that expression for P there, I just substitute it here. So what I get is x 1/square root of 2 pi integral over dx e to the power minus I px x okay, maybe I should integrate over y so not to confuse it with this x. So y. So what do I get here is 1/square root of 2 pi integral from -infinity to +infinity dy e to the power minus I pi y x y. This is a delta function. So what we get here is just the delta x minus y e to the power minus I pi y. And I already talked a bit about this. So in the end, what we're gonna get is e to the power minus I px and 1/square root of 2 pi. Because so yeah, so here the argument is you can change the variable here, right? E to the power minus I p. So one simple argument is just to say, oh, there is a delta here, then this only survives when x equals to y, and then we get the value of this function when y equals to x, so it's e to the power minus I px. The other way is just to say, oh, this is minus e to the power minus I p y minus x y e to the power minus I px, and then integrating this is basically doing the Fourier transform of this function, which would be, as we've seen, 1 by another argument, and then this is the part that is left here. But you can just forget about this consideration for now, and just look at this as the usual integration with a delta function. Okay. So then this was just the overlap between x and p. Then the modulus of this would be the modulus of this expression. Pi, and the modulus of the e to the power minus I px is always 1. So what we get is just the 1/square root of 2 pi, which does not depend on which basis elements p and x we have chosen in the first place. Okay. So this was a bit, yes.
You have to do a change of variables from y to y minus x to be able to integrate it.
I spoke about this.
Yeah, so we change the variables.
Okay, so this was, in principle, you can forget about it, but this is kind of a more rigorous way to see why this holds. Like, so the fact that we know is that the Fourier transform of delta is 1. And here what we do, so basically we know that the Fourier transform of delta of x is 1, but here we have x minus y. So we change the variables to bring it here, then we can immediately apply this argument, and then we are left with this here. Yeah, so that's basically the idea. Where?
Yeah, could you change your variables? This line x.
Delta function is symmetric. So delta x minus y equals delta y minus x. So yeah. Okay, one last thing is how do we transform the wave function from the momentum representation to the position representation and back, and how does it follow from our basis decomposition here. So psi of x is basically when we look at the overlap of the function psi, wave function psi, with the basis elements, with the position basis elements that we want to find the coefficient for. And the same for momentum. Okay, so then to find an expression which connects these two functions, one thing we can do, we first conjugate that expression. So what we get is the bra of p is 1 over square root of 2 pi integral dx e to the power minus I px x. So here's the plus and here it's the bra. And then we just multiply by ket psi on both sides. We get is p psi equals 1 over square root of p pi integral from minus infinity to plus infinity dx e to the power I pi x x psi. And from this, it immediately follows that we can write psi tilde of p as an inverse Fourier transform. So I'm just continuing what I've been writing there in the right corner. So we get that psi tilde of p equals 1 over square root of 2 pi integral dx psi of x e to the power I. And one can also show that the other way around is just a direct Fourier transform. So but here over dp, e to the power the psi tilde of p, e to the power minus I dx. And these are two expressions which connect the representations of the wave function in the momentum basis and position basis. And this trivially follows from the fact, like if you remember that the bases themselves are connected by the Fourier transform, then you can easily derive this. Okay, so in the exercise, you will need to apply this to one particular example of the wave function, which is the wave function, the ground wave function of the particle in a box. And we'll consider how we get to that solution, to that form of the wave function later in the course, when we'll start solving the Schrödinger equation for different potentials. But basically, you can see this as the following. So you have a particle which is confined in a box. And by confined, we mean here, what it means mathematically is that the potential in which the particle is only 0 in this box. So only in the region from minus L/2 to L/2, where L is the length of the box. It's a one-dimensional box. And in all other places, the potential is infinity, which means that which basically means that the particle can only be somewhere in a box. But we don't know where exactly. So if one kind of solves the Schrödinger equation for this potential, you get a variety of solutions, and the first solution with the smallest energy basically is so-called ground state solution, and in this case it has the following form. So it's gamma cosine phi x over L for x, which is from minus L/2 to L/2, and is 0 otherwise. Which makes sense because the particle only lives within this box. So the first thing you have to do is to normalize it and find gamma. And the second thing is using the formulas for using the formula for how we go from the position representation to momentum representation. You'll need to find this wave functions representation in the momentum basis. And also calculate the average values of x and p. So the average value x is basically the average value of the position operator, which is evaluated on this function psi1, and the same for momentum. Actually, one is on can already guess given the shape of the wave function. So from here, from the shape of wave function, because it's a cosine, and cosine is symmetric with respect to the origin of the coordinates. From this, you can already infer that actually the the average of position of the particle. So if you measure it, will be 0. Okay. And the last exercise concerns how you write the position operator in momentum basis. So in the lecture, we've seen that the momentum operator in a position basis, or more like when we ask the question, how does momentum operator act act on the wave function in a position representation, it actually just maps psi of x to minus IH, the derivative with respect to x, psi of x. And here you need to carry out the similar procedure and show that the position operator, when being thought about in the momentum representation, basically maps the psi tilde of p to something very similar. So it's going to map it to IH d by dp psi tilde of p. And based on this, you will need to write how does the expression for the average position look like for the as a function of psi tilde of p. Like, what do you need to integrate in terms of position, in terms of momentum representation? Okay, I think that's it for today. If you have any questions, they're very welcome. Otherwise, you can also just email me.
I have a question also regarding the delta function.
Yes,
It
please.
was in the first exercise, it was already
Yes.
was kind of tricking my mind. So in my understanding now, what I have of the delta function, I can write. I now